We're going to finish the lectures for Chapter 15, Solutions, with solution composition or normality, which is similar to molarity, but it's different, and it's a little confusing, so pay close attention to the lecture and slow down when you do your problems. Make sure you're thinking through it correctly. We're going to finish Chapter 15, Solutions, with the last section, Solution Composition and Normality. Normality is similar to molarity, but you need to pay attention to the description and the we're going to finish Chapter 15, Solutions, with the final lecture, and this one is in Section 15.8, and Solution Composition, which is like we did in 15.4 and 2 and 3, and we talked about an introduction, mass percent, and molarity, but it's going to finish with normality. So you need to pay close attention. It can be confusing. The calculations are very easy to do and similar to molarity, but you need to know the difference between the two. So normality is a unit of concentration, and we talk about normality when we talk about acids and bases. An acid's one equivalent of an acid is the amount of acid that furnishes a mole of hydrogen ions. One equivalent of a base is the amount of base that furnishes 1 mole of hydroxide ions, because by definition, an acid is a hydrogen ion donor, and a base is a hydroxide ion donor. It gives up hydroxide ions. It accepts hydrogen ions. So it's a hydrogen ion acceptor and will split apart into hydroxide ions. So that's basic definitions of what we call an equivalent. Equivalent of an acid is how much the acid furnishes a mole of hydrogen ions. Equivalent of a base is how much of that base furnishes a mole of hydroxide ions. Equivalent weight is the mass in grams, because it's weight, so it's in grams, of one equivalent of acid or base. So once I've determined my number of equivalents, then I can change that to grams. Okay, let's take a look at this. H2SO4, sulfuric acid, has 2 moles of hydrogen to make 1 mole of H2SO4. 2 moles of hydrogen for 1 mole of H2SO4. So when this ionizes and this breaks into its ions in water, it is going to give us 1 mole of H2SO4 will give us 2 moles of hydrogen ions. A half a mole of H2SO4 is going to give us 1 mole of hydrogen ions. So a half a mole of H2SO4 is what's going to give us an equivalent of H2SO4. So what's going to furnish us a mole of hydrogen ions? A half a mole of H2SO4. And that should make sense based on the number of hydrogen ions per molecule that are dissociated into solution. All right, let's take a look at this. The molar masses and equivalents of weights of common strong acids and bases. And we use strong acids and bases because they completely dissociate and deionize in water. So hydrochloric acid, the molar mass, if I were to add up 1 hydrogen and 1 chlorine, is 36.5 grams. How many moles of hydrochloric acid would it take to give 1 mole of hydrogen ion? It would only take 1, because every time this breaks up, it's 1 hydrogen to 1 chlorine. So 1 mole is all it would take. That means the equivalent weight would be 36.5 grams. So if I measured out 36.5 grams of hydrochloric acid, I would get 1 mole of hydrogen ions and 1 mole of chloride ions, excuse me. Nitric acid is the same way. If I dissociate this in water, I have, for every 1 mole of nitric acid, I will have 1 mole of hydrogen ions and 1 mole of nitrate ions. That means that its equivalent weight is going to match its molar mass. So if I added these up, it'd be 63, and that's also its equivalent weight. H2SO4 is different. We talked about that in the last slide, because H2SO4 has 2 hydrogen ions for every 1 sulfate ion. So if I have 1 mole of H2SO4, I would be given 2 moles of hydrogen ions when it dissociates. So when the molar mass of the entire compound is 98, its equivalent mass, and let's go back to the slide before it, remember that the equivalent is the amount of acid that furnishes 1 mole of hydrogen ions. So in order to furnish 1 mole of hydrogen ions, I only need half a mole of H2SO4, because I get double my money on this one. So for every, for every 1 mole, I only need half a mole because I have twice as many hydrogen ions. So my equivalent weight is going to be half of my molar mass, which is 49. Back on the bases, there's only one hydroxide and sodium hydroxide, so it's going to be the same number. The molarity and the normality are going to be the same. Potassium hydroxide is the same way. So the molar mass is 40. The equivalent weight is also 40. Potassium hydroxide, the molar mass is 56.1. The equivalent weight is also 56.1. Let's look at what normality is when we give it a value. So normality is going to be the number of equivalents per liter of solution. Where molarity was the number of moles per liter of solution, normality is the number of equivalents per liter of solution. To find the number of equivalents, you take normality times the volume equals the number of equivalents over liters times the number of liters, and that gives you the number of equivalents. All that is manipulation of the normality equals equivalents over liters, just like we worked with molarity as moles over liters, density as grams over cubic centimeters. It's the same mathematical concept. So if barium hydroxide is used as a base, how many equivalents are there in 4 moles of barium hydroxide? If for every 1 mole, let's see if I can get my pen to work correctly. For every 1 mole of barium hydroxide, we have 1 mole of barium ion, and we have 2 moles of hydroxide ion. If I have 4 moles of barium hydroxide, I would have 4 moles of barium, and I would have 4 times 2, which is 8 moles of hydroxide. So how many equivalents are there in 4 moles of barium hydroxide? The answer would be 8. So a couple things to keep in mind. If you need to, go back to the page that explains the equivalents. That may help. And remember that normality equals the number of equivalents per liter, where molarity is the number of moles per liter. Try to keep those two straight with your calculations, and that finishes up Chapter 15, Solutions.